Hello, my Algebra 2 students. We are starting our new little mini unit on complex numbers. This unit is really short and sweet, but it's necessary before we get into Unit 6, which is quadratics. So consider this like almost like a warm-up unit for the next unit. So what complex numbers are? Well, if I think about in all numbers, any number I can possibly, think of, we'll make ourselves a cute little like Venn diagram here. We have one circle would represent all like the real numbers, right? And then we have something called imaginary numbers. And we'll talk about those within this unit. And then in the middle here, those are called complex numbers, which are a combination of the two, all right? So they are a combination of real and imaginary. So let's explain, like, what is this imaginary? And it's helpful to see a couple of examples to bring some understanding to it. So I'm going to say recall, simplifying radicals. So we're going back to, little algebra 1, saw some of this in geometry even. So if I ask you just to simplify radical 25, so I'm just asking you to take the square root of it. We know that that's just going to come out to be plain old 5, right? I don't need the plus or minus because I'm not solving, I'm just simplifying, right? With the second one, if I give you like something like radical 48, if it's not a perfect square, then you're taught to break it down into what is a perfect square times what's left over that are factors of 48. So like 16 is the biggest perfect square that divides nicely into 48 times 3. And so then we would take the square root of 16 and you get 4, radical 3. For a third example, if I ask you to take the square root of 0, right now I hope you're telling yourself in your head, well, square root of 0 is just 0. That's it. That's perfectly fine. Where we run into an issue is if I ask you to take the square root of something like this, negative 4. Technically, we can simplify it. But if I type right now into my calculator the square root of negative 4 and hit enter, what you should be getting is like a quit or an error non-real answer, because that's what we're talking about here. So you're going to end up with something that we identify as imaginary, but let's first write down it is a non-real answer, because we can't imagine a number that when you multiply it times itself, it comes out as negative, all right? And so the non-real answer is because you can't have a negative underneath the radical. That's the issue, all right? So with that being said, what mathematicians decided to do was, well, what do we do when this happens, when you get a negative underneath there? Well, they decided to create the imaginary letter I. And so when we have I and we put like a little curl on it there, we say that that's equal to any time you have the square root of negative 1. That's the definition of what I is going to be. So now if we take example 4, we can say, all right, well, let's split it apart. Let's break it up into a perfect square. So 4 is a perfect square, and then times negative 1. If we break it apart like that, we know how to take the square root of 4. That's just 2. And then this we are defining as I itself. So we'd replace it with I. And then you're just multiplying the 2. So this would be 2I. That's how we would now define that value. So what does it mean in terms of like graphing and all sorts of other things? We'll get into that in the next unit. But for now, because we have this new variable I that's defined as the square root of negative 1, we need to know how to manipulate it. So over here, I'm going to write the powers of I. And what I mean by that, if we literally raise it to different exponents, what does it come out to be? So let's start with 0. If we raise anything to the 0 power, it should come out as 1. That's no exception here. Right? If we take and raise I to the first power, well, anything raised to the first power is itself. So the first two are easy. If we take I and we square it, well, what I want you to think of is we said I is defined as the square root of -1. If I square that, well, squaring a square root, they're just going to cancel. And I would end up with -1 itself. All right. Next up, we got I cubed. I cubed. You can think of as maybe breaking it into two things that we know already. So like I to the first power times I to the second, because when you multiply the bases, we add the exponents, right? Well, I to the first we've defined as I, and I to the second we defined as -1. So if we take the product of those, you'd get -I right there. And then you can keep going. Now, I'm not going to make you do every power of I, but if we do a few more, I to the fourth, maybe we could break that up into like I squared times I squared. All right. Well, each I squared is equal to -1. So when you take the product of -1 times -1, we get +1. Cool. All right. What about if we do I to the fifth power? All right. Well, that could be like I squared times I cubed. All right, so just breaking it into smaller powers that we've already discussed. All right, so I squared was -1, I cubed was -I, and if you multiply -1 times -I, you'd get +I. And you could keep going. But what I want you to look at this point is, do we start to see a pattern? So we got 1, and then I, -1, -I. 1, I. Think about what would come next. Hopefully what you'd recognize is that the next thing that would happen would be -1 and then -I, and it keeps on going. So that means I to the sixth would be that -1, I to the seventh would be that -I, and so on. Right? So a pattern forms. So the idea that it's 1, I, -1, -I, and then it repeats. Now, I've seen people show this pattern a couple of different ways. One way to show it is to kind of create like a little, whoops, sorry, moving on you there. Create a little like clock. I have to always very carefully set up the clock so that I don't confuse you or myself. But if you think about with the little clock, what I mean by that, we're going to put I to the 0 here, and then give yourself almost like a little set of axes. All right, I to the first power, I to the second power, I to the third power. Okay. I to the 0 we said was 1. If you then go down to I to the first, that was I. If we go down here, I to the second was -1. I to the third was -I. And then the pattern comes back up to repeat. So then this would be I to the fourth, I to the fifth, I to the sixth, I to the seventh, and so on. So if you have a small number or a small exponent, like let's say I said evaluate I to the 10th power, you could just continue that pattern and say, okay, well, let's see. So I to the 0, 1, 2, 3, I to the 4th, 5th, 6th, 7th, 8th, 9th, 10th. This should be equivalent to I to the 10th power, and that's my -1 right there. Oops, I'm almost off the screen. So that would be equal to -1. Where this doesn't work out that well is if I ask you to evaluate I to like the 80th power or 87th or 205th power, you'd be sitting there wrapping around the clock for a while. So it gets a little obnoxious. So it's nice for the lower exponents. When you get into those higher exponents, I've got another way for you to look at this so that you don't have to just sit there and circle around the clock forever. Right? So with that being said, let me switch my papers because I'm out of room. All right. There are actually two little shortcuts that I can show you. The first shortcut is looking at that pattern with the exponents. So I will literally call it shortcut number 1. Let's look at the exponents. Right? What we can do is, since the pattern repeats every 4 terms, is you can take the exponent, divide by 4, since that's the number of terms for it to repeat, and the remainder becomes the new exponent. Now, when I say remainder, I mean like we're dividing. So a little long division. Remember doing remainders? Hopefully. So let me show you what I mean. So the one we just did, I to the 10th, if we do this kind of longhand, if we say, okay, let's do 10 divided by 4. Now I'm asking you to go back a little ways. It would go in twice and you'd multiply, and then you'd get a remainder of 2. We're going to do some other long division later this year. So this is a good little like preview for when we get to that unit. But that's a little ways away. All right. So this is the remainder here. So that means that I to the 10th is now equivalent to I to the 2nd power. So our remainder becomes the new exponent. And then I to the 2nd, that's -1. If we do it again with like a different example, let's say I give you like I to the 67th power, because I said this is better when you have larger exponents. Okay. If I do 67 divided by 4, let's see, 4 would go into 6 one time, and then we would subtract, bring down the 7. Ooh, is your brain like exploding thinking about like what, 4th, 5th grade math right now? All right, 4 goes into 27. Let's see how many times. 6 times, and then we would multiply 6 times 4 would give us 24. We end up with a remainder of 3. All right, so that means that I to the 67th power is the same. It's going to give me the same answer as I cubed. And if you go back and look at the page before, I'll slide the page before out here. I cubed, that was -I right there. All right. And so it's a good little practice right here. Right? And we could do this over and over and over again. I don't want to give you too many examples right now. What I want you to think of is you could do the long division, but you can also still do this pretty simply on your calculator. So like if we did, let me get that out of there, 10 and then divided by 4, which was the first one, you would get 2.5. So if I get a remainder of 0.5, that's the same as a remainder of 2, right? If I get a decimal of 0.5, say that correctly. Here we're saying this is remainder 3. Well, let's think. If we do 67 and divide it by 4, you get 0.75. That was a remainder of 3. Right? So what that means is if I give you one last example, just so you can kind of see all the cases. Let's do I to the 33rd power here. Right? If I take 33 and divide it by 4, that would go in 8 times. We get 32, and you get a remainder of 1. Well, if I grab my calculator and had done 33 divided by 4, there's that remainder of 0.25, all right? So as a little reminder, let's finish this guy though. I to the 33rd would be the same then as I to the 1st, which is just plain old I here, right? So if you want to divide on your calculator and not longhand, which I don't blame you, right? What you have to think of is if I get a remainder of something 0.25, that's the same as a remainder of 1. If I get 0.5 or 0.50, that's the same as a remainder of 2. If I get 0.75, that would be a remainder of 3, right? And now think about it. If you divide by 4 and it comes in evenly, there would be no remainder. So you just get a nice whole number. That's the same as a remainder of 0, all right? So there's a quick little like cheat sheet for you. With that being said, I have a second little shortcut for you, all right? On the calculator, there's an I button. Let me show you where it is. So above the decimal point, you'll see a little I. So come on over here. Let me slide my calculator up, and maybe I'll zoom in just for this right here. All right. So on your calculator above the decimal point, you'll see in blue that little I right there. That is a little imaginary number. So let me zoom back out and show you what I mean. All right. So if I want, we did I to the 10th before. So if I hit second and then the decimal, that I is going to appear. and then you can raise it to the 10th power, and there it gives you -1. If I do I and raise it to the 67th power, on my calculator it works. Depending on your calculator, if it's a little older, it may give you a little trouble, with the higher exponents. But it might work. And so you got to have to test it out. So depending on your calculator, I would grab your calculator and try it out to see, does this work on yours? Is it a little clunky? Where does it start to fail if it does fail? All right. But if it doesn't, what a nice little shortcut right there. Okay. So if you need to do the exponents, you're dividing by 4 and looking at the remainder. If your calculator can handle it, you can simply just take your calculator and raise it to that particular power, and it should work for you. Right? Now, with that being said, we said at the start of the lesson that we were talking about complex numbers, and we've only been focusing on imaginary. So let's finish off with the idea of what does a complex number then look like? Well, we said it's a combination. It's literally a real number plus an imaginary number. So the way it's written is typically in the form of A for the real number plus B times I for the imaginary number. That is typically how you're going to see it written, where A and B are constants. So a very simple example is it could just look like 2 plus 3i. That would be a complex number where 2 is the real number and then the 3i, that's the imaginary piece of it. Every single number can be written as a complex number. So even if I just gave you a plain old real number, like the number 5, and I said, okay, write it for me as a complex number. Well, if you only have the real portion of it, this would be the A part. And so then you'd have 5. If there is no imaginary part, then the B would just be 0. So plus 0i like that. So any number that I give you, real or imaginary, can be written as a complex little combination right there. Now, some of the examples you're going to see on the homework have some simplification, like the combination of what we did above, and then writing it in this complex format. If you have a little more space on your paper, obviously keep going. I'm going to hop to the next page just to show you so that I'm not all crammed in here. But the last ones we'll do here in the video would be if I said, okay, let's simplify one where we have numbers with the imaginaries. So 3 times I to the 9th power, and then plus 5 times I to the 30th. All right, so that you can see it one more time. You can try it on your calculator. Otherwise, over here, I to the 9th. All right, if I want to use the exponent, I can do 9 divided by 4. And that's going to give me a 0.25, which is the same as remainder 1. And so then that would be I to the 1st. If your calculator can handle it, do second and then hit the decimal point to get I, and you could raise it to the 9th power and double check your answer. Yep, right there. There's my I. All right. The second piece was I to the 30th. So I to the 30th. Same thing. I can do 30 and divide it by 4 because the pattern repeats every 4. Since I have a decimal of 0.5, this is the same as I to the 2nd power, right? And then, I to the 2nd power is going to be -1. You can double check your work. So second, I raise it to the 30th and see if your calculator can handle it. Mine can, so I'm good to go. That checks out. All right, now to simplify, we're just going to substitute in. So this would be 3 times I, and then plus 5. And then in place of I to the 30th, I'd put a -1. And so then this would give me 3i, and then 5 times -1 minus 5, which is perfectly acceptable. But if the question says write it in A plus BI form, which is a lot of times what it will say, we would just rearrange the order and write it as -5 plus 3i. So that here's the real piece, and then here's the imaginary part of it. All right, when we get together in class tomorrow, if there's any questions, jot down little questions in your notes, and then this way you can make sure to get them answered in class. Thanks, guys, for watching. Go answer that post-video question right now.